Hey, this is Charlie, and this is the Lab 6 humidity video. First up is the learning objectives for this lab. So here's the part where I tell you what it is that I hope you learn in this lab. I hope you find specific humidity. And for these lecture slides, I've made these into links. So if you click on it, it'll take you to the section in the lecture slides that just talks about finding specific humidity. So by the time you're done with this lab, you should be able to find specific humidity, find maximum specific humidity, find the dew point temperature, calculate the relative humidity, calculate and evaluate specific humidity deficit, and enter numbers into Canvas. So this lab has a whole bunch of new definitions. I'm really sorry about that. There's absolutely nothing that I can do about it. They're all important. And I've made a cheat sheet for you with some information, and I would probably, if you can, print it out. If not, I would make notes to myself about each step so that you can keep, for example, specific and maximum specific humidity separate in your head, and keep specific humidity and relative humidity separate in your head. Yeah, whatever you need to do, take notes. So let's go over the definitions. So first up, humidity is water vapor in the atmosphere, and I'll go over these more fully in a minute, but repetition is an important tool in aiding memorization. So humidity, it's the amount of water vapor in the atmosphere. Saturation is when there is as much water vapor as is possible, and if it gets cooled, then you get condensation. In fact, if a body of air is saturated, it is at dew point temperature. So as the air cools, the relative humidity goes up. When you get condensation, when relative humidity is 100%, that is the dew point temperature. Specific humidity is a measurement of the amount of water vapor present. It's just how many grams of water vapor you have per kilogram of air. As opposed to maximum specific humidity, that's the most you can have at a specific temperature. So maximum, it's the most you can have. Specific is just how much you have. Specific humidity deficit. Deficit means you're lacking something, so it's the amount of water vapor that you're lacking. It's the difference between what the actual specific humidity is and what the maximum specific humidity is. It's like how much more water vapor could the air hold? Relative humidity is how much water vapor is present compared to, relative to, how much water vapor could be. So it's really specific humidity divided by maximum specific humidity. Since specific humidity is how much you have, divided by the maximum, that's relative humidity. So humidity is just referring to water vapor in the air. It is a function of temperature. The higher the temperature, the more energy is available to evaporate water. That doesn't mean that there is more water. It's just that there could be more water. So the higher the temperature, the more energy is available to evaporate water. Saturation is when the relative humidity is 100%, when the air has as much water vapor as it possibly could. If you add water or cool the air, then you'll get condensation. Dew point temperature is the temperature at which a given mass of air becomes saturated and condensation begins. So if you've got a parcel of air and the relative humidity is 100%, that parcel of air is at dew point temperature. Another way of thinking of it, maybe dew point temperature, as the air cools, eventually you'll get dew from condensation. That temperature is the dew point temperature. And it's abbreviated TDP for temperature dew point. If the dew point is below 0, then we call it a frost point. It's not really important. If you've never seen condensation on anything in your life, here's a drawing of some droplets of water condensing onto a glass. And here's an example of frost, which is actually sublimation. It's when the gas becomes a solid. So it's not that the water vapor condenses to become liquid water that then freezes. It's going directly, it's depositing as ice, which is pretty cool. Specific humidity and maximum specific humidity. So specific humidity is how much water vapor is present. Specific humidity is expressed as the mass of water vapor in grams per mass of air in kilograms. So it's grams of water vapor per kilograms of air. 1 cc of water weighs 1 gram. So a cubic centimeter of water, which is about the volume of a sugar cube, a volume of water that's 1 cubic centimeter, weighs 1 gram. I love the metric system. So for this lab, again, I'm sorry, but all of the mass of water is going to be in grams and the temperatures are going to be in Fahrenheit because I think that makes more sense. I mean, if we're talking about grams of water vapor, you can just visualize sugar cube volumes of water. Yeah, and I hope that works. So 1,000 cubic centimeters of water weigh 1,000 grams. So if you have a liter or a quart water bottle, a quart of water is about a liter. I think it's 33 ounces of water are a liter, something like that. So a water weighs a kilogram of water. A quart of water weighs about a kilogram. A quart of water weighs about 1,000 grams. So in a quart bottle of water, there's about 1,000 grams worth of water, just to help you visualize the mass of water that we're talking about per kilogram of air, and a kilogram of air has a volume of about a cubic meter, or about a cubic yard. So a kilogram of air has a volume of about a cubic meter or a cubic yard. So if you imagine a blob of air 3 feet by 3 feet by 3 feet, that weighs about a kilogram. So when we're talking about grams of water vapor, we're talking about, oh, good, this is fun, sugar cubes of water per cubic yard of air. For example, specific humidity could be given as 10.6 grams per kilogram. That would just be the specific humidity. So maximum specific humidity is how much water vapor could be present at a given temperature. Doesn't mean you have it, it just means you could. So right now, you can see every time the temperature goes up by 10 Celsius degrees, or just about 20 Fahrenheit degrees, well, 18, right? Because 10 Celsius degrees are 18 Fahrenheit degrees. So every time the temperature goes up 10 Celsius degrees or 18 Fahrenheit degrees, the amount of water vapor that can be present, so the maximum specific humidity, doubles. At 32 degrees, you can have 4 grams of water vapor. At 50 degrees, you can have 8. At 68, you can have 15. At 86, you can have about 27. And at 104 degrees Fahrenheit, you can have 47 grams of water vapor, which is almost 2 ounces of water. So a quarter cup of water per cubic yard of air. It's an enormous amount of water vapor. And you can see as it gets colder and colder and colder, the maximum gets really, really, really small. Like this is 10 grams, so we're talking 5 grams. Yeah. The colder it gets, the less energy there is to evaporate water. And as the temperature increases, there's more and more and more energy available to evaporate water. So the maximum just about doubles every 18 Fahrenheit degree increase. Same deal. So to find the maximum specific humidity, if you know the temperature, in this case 68 degrees, you just find the temperature, although we're never going to do this because we don't have these. To find the temperature, so at 20 degrees, we're going to slide right. So at 20 degrees, well, 20 Celsius is 58. This is from the textbook I use, so it's not in Fahrenheit, but 20 Celsius is 68 degrees Fahrenheit. The maximum is 14.7 grams of water vapor per kilogram of air. 14.7. So if you need to find the maximum, all you need to know is the temperature that you're talking about. If you know what the temperature is, you just slide over and there's the maximum specific humidity. Dew point temperature. To find the dew point, you read the maximum specific humidity. So if I give you the maximum specific humidity, well, that's the way it works. So to find the dew point, you first have to know what the maximum specific humidity is. So in this case, 10.6 grams per kilogram. You're just going to, on the table, on the chart, slide to the left and look up the temperature, in this case, 59.0 degrees Fahrenheit. 59.0 degrees Fahrenheit. So if you know what the maximum specific humidity is, or actually, also the other way it works too, if you know what the maximum is, you know what the dew point is. If you know what the actual, this works both if you know that the max or if you know the actual. Like if I told you, hey, this parcel of air has 10.6 grams per kilo, what's the dew point temperature? You just look up whatever that gram, whatever the specific humidity is, slide to the left, and there's your temperature. To find the maximum specific humidity, if you know the temperature, so yeah, if you know the max or what you have, you can find the dew point. If you know the dew point, you find the max. That just depends which way. Which one do you know? Do you know what the temperature is? Well, at 32.0 degrees Fahrenheit, the maximum specific humidity is 3.8 grams of water vapor per kilogram of air. So if I told you what the max was, you'd know what the dew point temperature is. If you know what the dew point temperature is, all you got to do is look it up on the table, and there's the maximum specific humidity. Again, to find the dew point temperature, you read the maximum specific humidity. Oh, but what if it's in between? If it's in between, then you slide over and take the cooler temperature. Yeah, like in this case, we've got 4.8, well, we have 5 grams of water vapor. So the dew point temperature for 5.1 grams is 39.2. The dew point temperature for 4.8 grams of water vapor is 37.4. So in this case, for this lab, I mean, in reality, if you had 5, there's got to be a table, a chart, a formula that you could get the exact value. Let's do it a little bit more easily. So if I give you the specific humidity, and it's in between on the table, we're going to pick the cooler dew point temperature. Because we don't have 5.1, we only have 5 grams. So you're not going to get condensation when it cools down to 39.2. You'd get condensation probably when it cools down to like 38 or something like that. We're just going to use the next colder temperature on the chart. Just let's make it easy. The ideas are really more important than doing math. So if I give you the specific humidity and it falls between 2 exact values, take the colder temperature. Take the colder temperature. Saturation vapor pressure, I'm just going to talk about it super duper duper briefly. It's the amount of water vapor expressed in millibars. So millibars are how we express the actual pressure of the atmosphere. So what we're talking about is the idea that we're telling you how much pressure in the atmosphere is being exerted by water vapor. So it's the partial pressure. It's the part of air pressure being exerted by water molecules. So we have air pressure because the molecules bounce all around. If there's more of them, they bounce harder. So the air pressure is higher. But out of all of those molecules, up to 4% could be water molecules. So out of any cubic meter of air, it would have to be really, really, really hot. But you could have 4% of the molecules could be water molecules. So that would be the vapor pressure. Water vapor, just one gas in the atmosphere. Saturation vapor pressure, you just look it up on the table. We're not going to use it in lab. They do use it in firefighting. They also use it in agriculture in figuring out how much water plants need. They look at the vapor pressure deficit. We're not going to do any of that. We're going to look at specific humidity instead of looking at vapor pressure, because I didn't want you to have to learn a third thing that involves millibars and water vapor. Yeah, we can do the same thing with specific humidity. Relative humidity. It's what you've got relative to what you could have. Relative humidity is the amount of water vapor present, that would be the specific humidity, divided by the maximum, the amount of water vapor possible at that temperature. So temperature is a crucial component of relative humidity. So you have to know the temperature. If you know the temperature, you know what the maximum is. That's why you have to know the temperature, and you have to know the specific humidity. It's also expressed as a whole percent, like 77%. Amount present, how much you have, that would be specific humidity. Amount possible is a function of temperature, that's maximum specific humidity. So like I said, as the temperature goes up by 10 Celsius, 18 Fahrenheit, the maximum just about doubles. So at 0 Celsius, you could have a max of 4. At 10 Celsius, you could have a max of 8. So relative humidity, what you have, 4 grams divided by the maximum, 4 grams is 100%. So for this parcel of air, this blob of air, dew point temperature is 0 Celsius. If it warms up by 10 Celsius, the maximum doubles. So we still have 4 grams. That's an important concept. As the temperature increases, the specific humidity doesn't. As the maximum specific humidity increases with increasing temperature, the specific humidity, how much you actually have, doesn't increase. I mean, it could. Your blob of air could go over like a really hot lake and pick up a lot of water vapor. It could go over a jungle, pick up water vapor. But for these problems, the assumption is it's not. It's just getting hotter. You don't have more water vapor. It's just hotter. So now we still have 4 grams. Because it's 10 Celsius, the maximum is just about 8 grams. 4 divided by 8 is 50%. And then if it gets even hotter by another 10 Celsius, so if it gets up to 68 Fahrenheit, now the maximum is 16 grams. We have 4 grams. 4 over 16 is 25%. So as the temperature increases by 10 degrees, the relative humidity gets cut in half. At 0, it's 100%. At 10 degrees, it's 50%. At 20 degrees, the relative humidity is now 25%. So if, as the temperature increases by 10 degrees, the relative humidity is cut in half, the opposite happens when it gets colder. So let's say it's 5 o'clock in the afternoon and we start off with 4 grams, but now they're watering the soccer fields. And so some of that water evaporates and we have 5 grams. I'm going to ignore that for a minute, but just keep in the back of your mind that we have over 4 grams in the atmosphere because the math works better if it's 4 divided by 16, 4 divided by 8, 4 divided by 4. So it's 5 o'clock in the afternoon. As it gets colder during the night, at, let's just say 11 p.m., maybe it's down to 10 Celsius, and now we have 50% relative humidity. We still have 4 grams, but now the air can only hold 8 grams because it got colder. So now we're at 50% relative humidity, and if it cools down to 0, 5 o'clock in the morning again, then we have 4, the max is 4, the relative humidity is back up to 100%. So if in the afternoon it had picked up more water vapor, at some point it would cool down and we would have gotten condensation. Because the most you can have is 4. If we had more than 4, that water would have condensed out and become dew. Hopefully that wasn't too confusing. The most important part, if the temperature increases by 10 degrees, the water vapor stays the same, the relative humidity is cut in half. Every time it cools by 10 degrees, the relative humidity doubles. Warming equals drier relative humidity. So if it was 32 degrees and the max, so we would know what the max is. The max is 3.8 grams of water vapor. If it heated up to 68 degrees, now the maximum is 14.7. If we still had 3.8, that would be, 4 divided by whatever, 16, like close to 25%. Same example. The temperature has now increased by 10 Celsius, 20 Celsius. So the relative humidity goes from 100% down to 50%, down to 25%. Oh, there you go. We have 3.8. The max is 14.7. So the new relative humidity is 26%. As the air cools, you get condensation. So if it was 35 Celsius, that Celsius one snuck back in there. As you're doing the lab, I had to go through and converted all the numbers. I converted all the Celsius to Fahrenheit. So if you find one, let me know. 5 points extra credit. I think I got them all. Everything in the lab should be degrees Fahrenheit and Fahrenheit degrees. But for now, we've got at 35 Celsius, you could have 36.4 grams. So let's say it's 100% relative humidity. As it cools at 20, you can only have 14.7. So if we started with 36.4 and we cooled the air down to 20 degrees, then 21.7 grams, the difference between what we started with and the max at a cooler temperature, that's how much is going to condense. If specific humidity remains the same, but the temperature increases, so this is a plot, I think, from the Sac Airport of temperature going up and down and relative humidity going down and up. So as the temperature goes up, the relative humidity goes down. The hottest part of the day, usually the part of the day with the lowest relative humidity. If the specific humidity remains the same, but the temperature decreases, then the relative humidity increases. So we still have the same amount of water vapor, but it's cooler, so the max is lower, so the relative humidity goes up. The hotter it is, the more water vapor you can have. This is the distribution of water vapor across the planet. You can see across, that's convenient, across the ITCZ, where it's hotter and the ocean is evaporating a lot of water vapor. That's where we find the highest amounts of water vapor in the atmosphere, much lower amounts over the land and at higher latitudes. So it's another example. Yeah, it's just a function of temperature, but it's mainly latitude, right? If you looked, going north from the equator or south from the equator across the ocean, it's latitude as modified by high elevation for the Andes, the Rockies, the Sierra Nevada, the Ethiopian highlands, the Tibetan Plateau, some of the mountains in Papua New Guinea. They're because it's cool to be high. So these places it's high, so it's cool. Measuring humidity. We're not doing this because we're not in lab, but we would if we were in the classroom. We'd be using a sling psychrometer. As water absorbs heat, water evaporates, cooling the thermometer. So there's two thermometers. There's one with like some cotton, it looks like shoelace that's wet, and then there's a dry bulb. You spin it around, water evaporates. The drier the conditions are, the more water evaporates, and the bigger the difference between the two temperatures. If there's no difference between the two temperatures, nothing evaporated, the relative humidity is 100%. If there's a really big difference, then it's dry and the relative humidity would be very low. No temperature difference, 100% relative humidity. You're at dew point. Big difference, low relative humidity. Lots of cooling from evaporation means that the air is really dry. This is a hair hygrometer. I think Alizé talked about the role of humidity in making her hair get curlier and frizzier. So this is an actual scientific instrument that uses strands of human hair. There's a little weight, and you can calibrate these things by getting into a shower until you have steam, and then you adjust it and go, oh, yep, that's 100%. And then as the hair absorbs moisture, it gets shorter. And then it pulls on this and makes the dial go. As the humidity goes up, it's going to pull on it, so it's going to make it go up to 100. As it gets drier, it's going to stretch out, and it's going to show you what the humidity is. But it's a scientific instrument that has strands of blonde human hair, which I think is just crazy. Calculating humidity. Specific humidity, it's just how much you have. So not a whole lot of calculation with specific humidity. Relative humidity is what you have compared to the maximum. What you have relative to the maximum specific humidity. Temperature, dew point temperature, relative humidity, specific humidity. So let's start with relative. Relative is the amount of water vapor present divided by the amount possible. So the amount present is how much you have. The amount possible is based on the temperature. So to find the max specific humidity, you'll have to be given a temperature. So let's do an example. Find maximum specific humidity, find the dew point temperature given the specific humidity, calculate relative humidity given specific humidity and a temperature, calculate specific humidity given the relative humidity and a temperature. So it's one of those deals where if you know the temperature and the relative, you know the specific. If you know the temperature, you know the max. So if you know two parts, you know the third. So we'll find a maximum given the temperature, find the dew point temperature given the specific humidity. Given specific humidity and the temperature, you can figure what the relative humidity is. Given the relative humidity and a temperature, you can figure out what the specific humidity is. So if you know two, you can figure out the third. Calculate maximum specific humidity deficit. Yeah, so that's the last part. I'll go over that one last. So to find the maximum specific humidity, you just need to know the temperature. So if I told you, given a parcel of air at 77.0 degrees Fahrenheit, what is the maximum specific humidity? You'd find the temperature, slide over, and there's your answer, 20.0 grams per kilogram. If you had 10 grams and the maximum was 20 grams, 10 over 20 is 0.5 times 100 is 50%. So half divided by max times 100 expressed as a whole number is your relative humidity. To find the specific humidity, which is just how many grams of water vapor are present, I would have to tell you, for example, what the relative is and what the temperature is. So once you know what the temperature is, then the max times the relative is the specific. Let's see how that works. So we know the relative humidity and the temperature because I'm giving it to you. It's 77 degrees Fahrenheit. The relative humidity is 50%. What's the specific? Well, if it's 77 degrees, the maximum is 20 grams. So that's the most we could have. So specific humidity, like I said, it's the maximum times the relative humidity. So if it's 77 degrees with 50% relative humidity, 50% means we have 50% of the maximum specific humidity. The max was 20. 20 times 0.5 is 10 grams, or 20 divided by 2 is, well, no, 20 times 0.5. Yeah, that's better. 20 because the relative humidity was 50%, which expressed as a decimal is 0.5. So 20 grams of water vapor are the maximum. We have 50%, so half of 20 is 10 grams. 50% of 20 grams is 10 grams. Hey, there you go. So finding the maximum specific humidity deficit. It's the difference between the specific humidity and the maximum specific humidity. So, for example, I would give you the temperature and tell you what the specific humidity is. I could also give you the temperature and the relative humidity, and then you could calculate out the specific humidity because the specific humidity is just the maximum times the relative. But if I give you the temperature and the specific humidity, in this case 68 degrees, the specific humidity is 10 grams. So the specific humidity is 10 grams, and we look it up on the table and find the maximum is 20 grams. Then the deficit is 10 grams. So the specific is 10, the max is 20. The difference between the specific and the max is the deficit. So other examples of questions you'll have to do in this lab, find the specific humidity and find the maximum specific humidity deficit. So, for example, if I gave you the temperature, 86.0 degrees Fahrenheit, and the relative humidity, 15%, which would be very dry, we look it up on the table. At 86 Fahrenheit, the maximum specific humidity is 27.1 grams. 15% of 27.1, so 0.15 times 27.1 grams is 4 grams. So that's what we have. That's the specific humidity. We know what the max is because we had to look it up on the chart a minute ago. Hopefully we wrote that down someplace and kept it handy. So the specific is 4. The maximum specific humidity deficit is the difference between the maximum specific humidity and the difference between the maximum specific humidity and the actual specific humidity. So in this case, the max is 27.1 minus 4. So the deficit is 23.1 grams of water vapor. So the deficit is how many grams of water vapor would you have to add to get the relative humidity up to 100%? Just a couple more examples of how to do relative humidity, specific humidity, and dew point temperature. If you know 2, you can find the third. I mentioned this previously. So if you know the temperature and the relative humidity, you know the maximum specific humidity from the chart, and you can use that to find the specific humidity. Max times relative is the specific humidity. In this case, for this example. Let's say we looked it up. The max is 10 grams. The relative humidity is 50%. Then the actual specific humidity is 5 grams of water vapor per kilogram of air. If you're given the dew point temperature, you can find the specific humidity from the chart. So you find the dew point temperature, 77 degrees, and then slide over to find the specific humidity. In this case, 20.0 grams per kilogram. To find dew point temperature, you use the chart of maximum specific humidity. The actual dew point temperature probably is going to be between two temperatures. Use the lower temperature since condensation won't begin until it cools to the lower temperature. So to find dew point temperature, we're going to use the chart. For example, I find the specific humidity is 7 grams, so I go to the chart. 7 grams is in between 48.2 and 46.4 degrees Fahrenheit. So I'm going to use the cooler temperature. If we've got 7 grams, you won't get condensation at 48.2 degrees. It'll be lower than that, like probably 47. But for this class, if I said the specific humidity is 7 grams, what's the dew point temperature? Slide over and take the cooler temperature of 46.4, since you won't get condensation when it cools down to 48.2 degrees, but you'll definitely have condensation when you cool it to 46.4 degrees. So the dew point temperature with 7 grams per kilogram is 46.4 degrees Fahrenheit. To calculate the specific humidity and then use that specific humidity to find dew point temperature, we're going to use the chart. If the dew point temperature is between two temperatures, use the cooler temperature since condensation won't occur at the higher temperature. You haven't cooled it down to dew point yet. Relative humidity, if you know the temperature, and specific humidity, you know the dew point temperature from the chart, and then you can find the relative humidity. So specific divided by max is relative. In this example, specific humidity is 5 grams, the max is 10, so the relative humidity would be 50%. If you know the temperature and the dew point temperature, you know the specific humidity and max specific humidity from the chart, and you can find the relative humidity. So if I tell you what the temperature is and the dew point temperature, if you know what the dew point temperature is, you know what the specific humidity is. If you know what the temperature is, you know what the maximum specific humidity is. Both of those, you just look it up on the chart, and then you can find the relative humidity, because relative humidity is specific humidity divided by the maximum specific humidity. So in this case, specific humidity was 5 grams per kilo. The max was 10. The relative humidity is 50%. The dew point temperature, we're going to look it up on the chart. Specific humidity, you can look that up on the chart to find the dew point temperature. Maximum specific humidity, if you know what the temperature is, you look that up on the chart and it will tell you what the maximum specific humidity is. And then relative humidity equals the specific humidity divided by the maximum specific humidity. Entering numbers in Canvas. So most everything you're going to round to one decimal place. Is it a temperature? Is it a dew point temperature? Specific humidity, grams of water vapor, maximum specific humidity in grams of water vapor? Just round it to one decimal place. 47.6 degrees Fahrenheit. 5.5 grams of water vapor. Again, the Canvas bug, if you were supposed to, if you got a value of 10.0, don't worry about it. Just enter 10 Canvas. Yeah, don't worry about it. It'll never be wrong in this class. At least it shouldn't be. If it is, let me know, and that's 5 points extra credit for letting me know. Relative humidity, round to a whole number. Everything else, round to one decimal place. 33%. That's it for the video on Lab 6 on humidity. I wish you good luck. If you have any questions, please, please, please come to Zoom. I beg of you. This is another good example where like 5 minutes of conversation would help you get everything straight in your head and allow you just to breeze through the rest of the lab. Easy is good. Good luck.